project, it's a cloud pipeline for breast cancer diagnosis and treatment recommendation. The background is I had a project in database class. I built an integrated relational database for precision medicine. So there is a breast cancer data warehouse sitting on my personal computer. The data was simulated and quite small, but in real world, the clinical data and the genomics data tend to be very large scale. And the data size grows so quickly that it outgrows a single machine's capability very quickly. So the solution is we migrate to cloud, and we think that will be an optimized solution for our applications. So I will start with some motivation and the challenges on premises and why we need cloud. And then Michael will talk about the architecture, migration approaches, and the pipelines. And then and we also build some machine learning model. Deepti will talk about the machine learning model performance evaluations. So because probably not everyone know about what precision medicine is, so I want to give the definition. It is the individually tailored therapy based on the patient's disease subtype, so that the doctor can determine the most appropriate treatment for the patient based on their unique disease profiles. The advantages that we can avoid unnecessary treatment to save money for the patient and reduce toxicity, the side effects, and also significantly improve the clinical outcome. We can also utilize machine learning to predict cancer drug responses. This is actually my job. Currently, my role as data scientist is build machine learning models to predict cancer drug responses. So there are a number of approaches, including but not limited to drug sensitivity, genomic testing, biopsy, immunophenotyping, image tests. All those methods generate a lot of data, especially the genomic tests and the image tests. So there are four.
Can you go back to the previous slide just one second? I just wanted to see. Okay, yeah. That's fine. I got it. I wanted to see the last part. Thank you.
This one?
No, not continue. Sorry. So yeah, I got what I wanted to see. Thank you.
Sorry.
No, you're good. You're good. Thank you.
So there are four well-defined subtypes of breast cancer and one unknown type. So by differentiate those different types of breast cancer, the doctor can give the patient unique treatment for each type. So the outcome will be improved a lot. Here is a workflow of precision medicine. Basically, we take the sample from the patient, the tumor sample, and then we do a variety of tests, genomic tests or histopathology. And then we analyze those data, build models to predict the clinical outcome, and then this is the treatment selection part. It involves a lot of machine learning. So because the workflow I mentioned, we can see data integration is very important for precision medicine. Because we need a systematic and big picture in order to make the best decisions. Therefore, it's actually increasingly important to have an integrated database for those type of data. However, there is no public integrated bioinformatics database available. So many companies end up build their own database, including my company. So, however, if we build the database within a company, the data size usually be a problem. For example, for each patient, the whole exome sequencing data can reach 10 to 15 gigabytes. So if you have over 100 patients, it will be petabytes of data. Usually, many institutes and companies may not have a supercomputer or data center to store and build models with the data size of terabytes. So this is one of the challenges on premise. As we can see, the genomic data grows so fast in the past decade. There's only 1 terabyte of genomic data in the public database SRA, and then nowadays it's already over 10,000 terabytes. So, excuse me, you can see the data grows so fast that it outgrows the single machine's capability very quickly. On the other hand, cloud can provide us the scalability and the flexibility for this fast-growing data. In addition, cloud is also an ideal platform because it's high security and high availability. The doctors, patients, and the data scientists may be in different regions or different countries. But with the cloud platform, they can share that information for diagnosis and treatment recommendation very easily. So we decide to use Google Cloud for our project because it's I like the user interface. It's very user friendly, and also we get the free credits. And there are many other motivations I'm going to talk about on the next slide. So basically, Michael moved our database onto the cloud in BigQuery, and I created a random forest classifier and also a k-means clustering for patient stratification. And also, we created a logistic regression in BigQuery machine learning. And also, Deepti, she created a neural network in TensorFlow. She will talk about the model evaluations later. Due to the limited time, we may not be able to cover all the topics, but so the k-means results we do not include in this slide. If you are interested, I can show some results later in Q&A. So the advantages about Google Cloud is not limited to the low cost of data storage. One thing I like most about Google Cloud is its cloud machine learning engine. So if you develop custom machine learning models at scale, it has very high cost flexibility. It is a serverless system. It auto-scale on demand, and you can get as many machines as you need. And it also have a very cool feature. It has a parameter servers with a shared memory, which means it's not simply a map-reduced parallel computation. It actually lets the trainers to learn from all the others. So it's very cool. And also, if you develop interactively in Python, you can use Cloud Data Lab. It looks kind of, it looks the same as the IPython notebook, but I find it's very interesting because you don't need to manage the environment like IPython notebook. You need to pip install or conduct update all the time for new packages. But in Cloud Data Lab, it's very convenient. It has most of the packages we need, like the sklearn, Seaborn, a lot of packages. So you do not need to worry about the environment, and it's very easy to share and collaborate, and your co-authors can work on the same notebook. And also, it's very easy to scale up for fast training time. You can change the number of the type and number of machine you need very easily. You can also use the G-Cloud command to submit the machine type, like scale tire options for basic standard or basic GPU or TPU. So I'll hand over to Michael for the migration steps.
Thank you, Lei. So as Lei mentioned, I'll be walking us through the different cloud migration steps that we took, as well as some of the components to our data pipeline. You can see here a visualization of our cloud migration strategy. So evaluate, access, security, move the data, move the applications, and finally optimize. I'll be walking through each of these 6 steps in a little bit of detail. Next slide, please. So as you saw in the previous slide, our first step is to evaluate. So in this step, we took a pre-assessment. So what do we have? We have a MySQL database with biopsy and genomics data, as Lei mentioned. So we have data around breast cancer tumor biopsies, dimensionality, things like that, as well as genomic sequencing data. Additionally, as she mentioned, there was a machine learning model running in Jupyter Notebook. All of this was running locally on premises. So based on that, we mapped this out to our needs. What we needed, first of all, was the data landing zone, a way to get the data onto the cloud quickly and securely. We also needed a transformation and rationalization pipeline, so something to cleanse the data, conform it, get it into a cloud-friendly format, as well as a lab environment to test the ML pipelines. So this is the notebook server that Lei was referring to, so something that we could scale up as more data or more models were added to our application, and then something that could also write back to our data warehouse, so that we had both sort of a raw layer and a transformed layer, so that we could examine sort of both sets of data. Eventually, we would want a Hadoop cluster to actually run our machine learning pipelines. So once we deployed those and wanted those running in a more automated fashion, that's what we would use that for. And finally, an end state dashboard. So in the interest of security, we would have essentially one input and output controlled by the IAM layer. So whether that's uploading new data or examining the data in Data Studio, we would have controls for both of that. So next step, please. We can go to the next one. So a quick view of our architecture. So as you can, I want to draw your attention to the left side of the screen. As I mentioned, we have a layer of cloud IAM to control access for both data analysts and data scientists on GCP. So we've created a VPC within our network with some subnets contain, some subnets contain the ETL pipeline to make sure that that runs securely when we're updating our data. We also have access through the notebook server to Cloud Data Lab, and finally Data Studio, as you can see there in the center, to actually access and create visualizations of the raw BigQuery data, as well as the output from machine learning engine. So our next step was to actually move the data. We use Google Cloud Storage for this. As you can see, we have a bucket that we created that contains the data files as well as some of the code that we wrote for our pipeline. This essentially acted as a landing zone as well as a staging zone for landing the data and then transforming it to land it into BigQuery. Next slide, please. This is a visualization of the underlying algorithm behind our data pipeline. So what we used was the Apache Beam API for data flow. So running Python code on data flow to run the data from GCS to BigQuery. This is a visual representation of the directed acyclic graph algorithm, or DAG, that was running under, that's sort of the underlying logic for how data flow moves data. So kind of similar to how MapReduce has mapper tasks that eventually reduce down. The way a DAG works is it has what's referred to as nodes, and that's these individual tasks or squares here. And each one is directed to sort of move on to the next one in each of the API calls that I have to kind of move the data through each stage and finally into its output. The neat thing that I like about DAGs is because they're acyclic, you can kind of break them. You can have sort of a directed flow as you see in the middle, or you can kind of split them off and reduce them back down towards the end. And they're also very easy to parallelize. So it's kind of a neat sort of alternative to MapReduce. Next slide. Yeah. And finally, here's a quick representation of the data warehouse that we built in BigQuery. As I mentioned, we have sort of a raw layer that contains both our untransformed, or our cleansed data, so that's our genomic and biopsy data, as well as some flattened structures that are based on some BigQuery jobs that we built. Additionally, we have a transformed data in our model schema. So that contains, as you can see, there's 3 tables that contain data around a random forest output. One neat thing I'd like to call your attention to, so if you look at the breast cancer logistic regression object there at the top, that's actually a model that is stored within BigQuery. So BigQuery has some really neat capabilities where you can essentially go in and build some rudimentary linear and logistical modeling within the UI itself. So think of it as sort of like if MySQL had machine learning functions built in, you can actually build those directly in BigQuery without going to like a notebook server or using, you can use it with just SQL, which is, I think that's pretty cool. Great way to sort of quickly run some predictive analytics on data. Next slide, please. So that's about the gist of moving our data and applications into big GCP. So now I'm going to pivot over to Deepti to give us a little bit of understanding of our machine learning models.
Okay, thanks, Michael. Lee, can you go to the next slide? So the machine learning model, there are like different steps we have, like where we have the input data, we do the EDA, and then we do the pre-processing and the feature engineering, and then we have the model evaluation. And later we validate the model and then we deploy it. Lee, can you go to the next slide? So as a part of the process, we did the same thing. We did the EDA and feature selection using Data Lab. And we identified whether how the predictors are correlated with each other. And it gives a little metadata about number of variables, how many observations, how many are missing. And the whole idea about the ED and the feature selection is to make sure that we pick the appropriate features and there's no multicollinearity within the variables. Since we have 30 variables, we have to be very careful when we are picking the model. Go to the next slide. So what we did is like we created 3 models. One is logistic regression, since this is a binary classification. So we have the random forest, which we did it in BigQuery, and the neural networks we did it in TensorFlow using the Python, and we call the TensorFlow API. Can you go to the next slide? So each model has its own accuracy based on the basic model which we picked up. So the logistic regression has around 97.46, random forest 93.71, and neural network 81.32. Even though it is less, neural network has certain hidden layers within it. So this can be further evaluated by adding more complexity to the model by including the interaction between the terms. Lee, can you go to the next slide? So the conclusion is like the project itself is about like lift and shift to the cloud. Making sure we have the enhanced capabilities from the cloud, which we can leverage, and also deploy the model which is running in the local machine. We converted into different models on the cloud computing side, and which is done very quickly based on the data. So what we conclude is like the cloud capabilities, the migration methodology, and integration and visualization and monitoring are part of the migration methodology which we created, and we experienced it as we are migrating the data from local machine to the cloud. And in the ML side, we have different models and we have different performance, but supplementary evaluation with more additional features and data needs to be done. And advanced research on model and complexity needs to be done because currently we did with a small data set and with a simple model. And can you go to the next slide? So all of our code is on the GitHub, and that would be it from the presentation standpoint.
Great job.